All right, welcome everyone. This is a fairly special class here because this is our first year in this new building as the Unified CUNY School of Public Health. So there are a few little glitches like emails and logins. It's because things are really, this is a new school. It's been formed from several different schools. I myself was at the Hunter College School of Urban Public Health, along with Tony DeVito in the back here. And we taught this, the equivalent of this course down at Hunter for the last 3 years. But this is our first year now teaching it up here on 125th Street. So, so that's exciting. And it's also, hello. It's also always exciting for me to get to meet the new incoming epidemiology and biostatistics class. I myself am an assistant professor of biostatistics. Just to give you a little bit of background about me, I am from Canada originally. I went to school at University of British Columbia for my undergraduate, University of Waterloo for a master's degree in physics, University of Toronto for my PhD, and then I was a postdoc at the Ontario Cancer Institute and a postdoc at the Harvard School of Public Health and Dana-Farber Cancer Institute before going to Hunter College and now finally here. So, so it's been a long route to getting around here. I'll tell you a little bit more about my research as we go along. So my main area of research, and part of the reason that I tell this to you is that I have an active research program, and I'm always looking for interested students to get involved in it. So just to give you an idea, this is some bullet points of trying to summarize a lot of different things on one slide. But my general area of research is what we call high-dimensional statistics, where you have more measurements or more variables than you have observations. But that's kind of abstract. The kinds of real things that I work on are cancer genomics, HIV, and human microbiome data. And these are all types of data where you use high throughput modern equipment to collect a lot of different data on a few specimens, and it requires these types of methods. I'm also pretty interested in technology in the classroom and have been experimenting with Tony over the last few years about ways to deliver this course that will be convenient for you and will provide as much flexibility as we can for you and work easily in the class. So that brings me to the format of the class. It's a somewhat non-traditional hybrid format class. So the way it's going to work is we will come here every week and deliver an in-person class. Sounds like it's working, Tony? Good. Because in my experience, there are always at least maybe half of the class or so who really prefer an in-person lecture. And so we will be doing that. But then there tend to also be about half of the class who, for one reason or other, would rather have other options. So we are right now streaming this live over our YouTube channel as a Hangout on Air. So if you are somewhere else, you can watch this on your phone, on your whatever. You can watch it live. We have a module set up so that you can type in questions, and they should appear right here on the screen, and then I'll answer them during class. And if you show up late to class while online, you can watch at double speed and catch up to where we're at. It's kind of neat that way. And as soon as the class is over, it will be there and be recorded so you can watch it again later. Or if you can't watch it during class, you can, if you have to miss class, it's okay. You won't miss anything except some opportunity to ask questions in real time. But the lectures and the labs will all be there on our YouTube channel. Which reminds me of a few other things I wanted to tell you about. I'm active here in, I've started a couple of clubs that have been going for a couple of years. They're a lot of fun. The CUNY Predictive Modeling Club. We have a Google group, but lately the more active thing that we've been doing is the Statistical Learning Book Club, which is we meet every week and someone takes a turn reading a section from an interesting book. We've been working on a book called Data Analysis for the Life Sciences lately, which has a lot of methods that are relevant to my research, and it's just an interesting book. Hi. And while I'm thinking of it, I've also set up a Google group for our class, and you'll find that underneath the course information. Please do sign up for that. I've found it seems to stimulate discussion and be easier for a lot of people than the Blackboard discussion boards. You can either use it as an email list or as a board if you don't want to get any more emails, but it's there. We will continue making all essential course announcements through Blackboard. But this Google group will be for other things like questions about assignments, about exams, things of general interest. We do tend to get very overloaded by email during the semester. So if you have a question for me that is of something that I know a number of people will be asking me, I probably will just reply and say, will you please post this to the discussion group so I can answer it for everyone. Question?
I was just going to ask about the Statistical Learning Book Club. Does that go like beyond like the level of statistics here in terms of like knowledge in other math subjects, like calculus-based statistics?
Yeah, so we have tried to cover books that that don't require a specialized background. These are introductory books, but they also cover topics that are not covered anywhere in our curriculum in the MPH program here. So, which was kind of why, you know, my initial motivation for it was I wanted students who would be trained to do some of the research areas that I work in, and particular things that we just didn't have in our program. So things around predictive modeling that we don't really cover, also around high dimensional data analysis. Also learning R, the statistical programming language that is primarily used in genomic and a lot of other areas of statistical research. So no, you don't have to let a lack of background stop you from joining. Currently this group, we're meeting every Friday mornings at 10 a.m. Oops, I keep on hitting the wrong one there. So I'm not assuming any prior knowledge of statistics here. I know there are always some students in the class who might be dismayed by the slow pace that we get started at. I really start from the basics and go pretty slowly for a while. And this is just to help get everyone up to speed and try to get everyone onto a more common footing for your next class, Biostatistics 1 next semester, because we do often have students coming in with very different backgrounds and levels of data analysis and statistical background. So if you if this course is going to be very basic for you, and I know there are some people in here who that will be the case for, I would encourage you, we'll talk a bit more about statistical software, but I would encourage you maybe to take the opportunity to try a more advanced statistical software package, namely R. It's one that I have a lot of expertise in. I'm a developer and contributor to the project. And I will support as much as I can anyone who is using it. You'll see later from Tony the language that we will use in labs is SPSS. It's a nice graphical, user-friendly introductory package. That's why we use it. The only thing is it will be used for a couple of courses and then not anymore. It's really it's for introductory purposes. Yes.
Do we ever cover SAS
Yes, you will learn SAS starting next semester in BIOS 1. They introduce you to SAS, and you'll use SAS in a number of classes. So yes, and this is, I'm glad to see already you're not afraid to ask questions. Don't be afraid to ask questions. I have a way of making any question sound like a smart question, hopefully, so you'll never feel dumb about asking a question. I want it to be a really welcoming and comfortable learning environment. Don't be afraid to ask questions. It enriches class. Sometimes I'll reach out and try to get fish for questions, but you definitely should never feel shy about asking. So we're going to have 2 exams during the semester. They're in your syllabus. In those ones, you will come in and you'll have the entire period with a computer to do an exam, some of which will be just knowledge-based and some of which will be data analysis-based. We'll give you more information and some examples of what to expect as the exam dates approach. And at the you'll have homeworks throughout the class. Do the homeworks. They're important for your learning, and they're also important for us just seeing that you're participating and being active in the class. And then at the end of the semester, and this is really fun, we've done this a couple of times now, instead of a final exam, we got rid of that, and we're going to have a final project that will involve a more real-life type of data analysis, and you'll prepare a poster, and we'll all get together and do poster presentations during that final class, and that will be the final part of your assessment. It's lots of fun, and if you have data sets, projects of your own that you want to do, you'll be welcomed to do that. We'll give some example data sets and projects that you can use, but you are by no means limited to those, and very much encouraged to come in with a project that you're interested in doing. So what you can expect from us, normally we will start class at 5 p.m. promptly. So be here on time if you can. I'm not going to get you in trouble if you can't. You're all graduate students, and class will be recorded. So if you miss part of it, you can catch up on it later. But I started on time to make sure that for most of you, you'll get the full class period that you came for. Will be available for you. We really aim to be accessible and available. The Google group is an excellent way to ask questions about the course, about anything of potentially general interest. If you have something that is really specific to you, like I can't make it on this exam date because of something, or I can't hand in this homework because of something, you can let us know those kinds of things by email. And I am available for individual meetings by appointment. I've found in the past that seems to work better for most people than trying to set an office hour. And you'll see a link on Blackboard where there's a web page where you can just automatically book an appointment with me if you want to do that. And you should expect a supportive learning environment. If there's anything that is making you uncomfortable or shy or anything, and there's something that we can do about it, please let me know, let Tony know, and we'll do what we can, because that is really our goal, and for you to have a positive first experience here in your program. So what are you going to come out with today? You've already accomplished learning objective number 1. You've been able to you've found the lecture room, and in fact, the lab room is the same right here. So good job. You'll learn a bit about the pros and cons of SPSS and our software. You'll start learning a bit about SPSS during the lab session today. Yes?
Sorry, if you're familiar with SAS, which one of these programs is more similar or no?
Neither of them are similar to SAS. Okay. You can use SAS if you would like to, but no, really, I guess in a way, R is more similar to SAS, just in that it is a programming language. But it's completely different than SAS. It I don't know, doesn't help you that much. One other pro that I mentioned, but it bears mentioning again, is if you would like to get involved in any of the areas of research that I talked about, I highly encourage you to get started learning R as soon as possible, because it's essential in these areas. Let's see, we'll go over the syllabus a little bit. Actually, if I remembered to put it on this computer. We'll have to see. That might be a little bit of a challenge right now. We might have to do that afterwards or during lab. And then a little bit of statistics, identification of important types of data, types of variables, and types of graphs for representing those in tables. We do have a textbook. It could be optional, but we made it required because it's free anyways. It's a nice textbook. I have looked at many textbooks, gotten desktop copies of $100 textbooks, and I still like this one quite a bit. It's concise. It's not a biostatistics textbook per se. It's just a statistics textbook, but it's fairly concise, and it is free. You can just download the digital copy for free. There are a few options for ordering a printed copy if you prefer that. But yeah, it's free, and it's an open source textbook. And so if you report any errors or problems that you have with the textbook, or that, I can report those back to the author, and this author, David Diaz, puts out new versions pretty frequently, so they will end up back in the textbook. It's kind of a neat model. I guess before I get started, are there any more questions about the class, about, I don't know, about today? Yes.
I'm sorry.
It's okay.
I didn't catch your name.
Oh, sorry. I'm Levi Waldron, and I'm. You can call me Levi. You can call me Professor Waldron, whatever you like. It doesn't matter to me. But I hope to get to know some of your names during the semester as well. It takes a little while, but come up and introduce yourself to me maybe as soon as lecture is over. And I'll start getting to know you as the semester goes by. Yes?
Hi, Dorothy as well. For the homework, are they going to be done through SPSS and R?
So the homeworks you will be able to do using whatever software you want. Like, there will be questions asking you to calculate some statistical thing. You could use SPSS, you could use R, you'll get the same answer. So it's really not an advantage or disadvantage to you for the assignments or exams which you choose. Yes?
My name is Arash.
Hi, Arash.
So if someone just wants to learn R
Yes.
and don't bother with SPSS,
Yeah.
so you can get away.
Yeah. Yeah, you can get away with that.
So what's the best way to learn R?
Well, let's see. Maybe I'll pull up. I have a few ideas about that. Come on, where is? So here on waldronlab.github.io, I've put together some resources that I found useful for people in my lab, also coming from recommendations from people in my lab. And one of them is learning R. Whoa, what happened there? Here we go. This data camp is a nice introductory course, although you have to pay something if you want to take higher levels of courses. This swirl is really neat. It's actually an interactive teacher that you install a library within R, and it teaches you R from within the environment. I like it a lot. I would probably recommend those ones to get started with, the data camp and swirl. And some of these other ones like QuickR, they're useful references for looking some things up. There are so many resources for learning R now. It's a bit overwhelming. The challenge here is trying to cut it down a bit. One thing to make sure if you're learning R is to install RStudio as the environment. And I can yes?
You want to put the syllabus on there while you're back out?
Oh, have you got it on the key? All right. Thank you. Danger in class. Yeah, let me know if you're planning to learn R during this course so that I can give you some additional information. Oh.
Sort by data should be at the top.
That's, I don't see it.
It should be right at the top if you sort by date. It's both inside a folder.
Oh, inside a folder? Which folder?
Yeah, the folder says BIOS syllabus, BIOS 611 syllabus.
Ah, got it. Thank you. Okay. Let's see. So I've shown you most of this stuff so far. That's too much stuff to show you. Mostly, so you're going to have those 6 homeworks cumulatively worth 30%, 2 exams worth 15% each. This final project worth 30% because it'll be probably more work than the exams. And then class participation for 10%. I will take attendances in class, but that's really just for our curiosity to know who is coming in person and who is attending online. You're not required to do that to attend to get full grades in class participation. Just have some sort of evidence that you know that you are attending, and as long as you're attending online and or in person, doing your homework assignments, and maybe posting occasionally to the discussion group, or just anything so that we know you're actually participating in the class. Standard grading system. We have a policy for late and incomplete assignments. If you are having a problem during the semester, let us know as soon as possible, and we can be accommodating, but you do need to be in touch and let us know what is going on. The syllabus here will tell you which times you have to attend in class. Today, because we were not at all sure whether the AV and everything would work, and I want to have a chance to get to see everyone in person at least once, until October 6th is the next time that in-class attendance is mandatory for your first exam. Second one is November 14th, and then your final project presentation will be on December 19th. So you can put those in your calendar and plan on attending in person on those days. Otherwise, it's up to you. There is also, I put in a little primer on statistical notation in the bottom, which can help as we're going on to remember what some of the symbols are, and things like Greek versus Roman letters. We use Greek to represent things about a population, and Roman letters, regular letters, to represent things about a sample, which I'm going to tell you about now. By the way, if you haven't gotten the attendance sheet yet, please make sure that you get it and sign it sometime before you leave today.
Is that different from the computer sheet?
Yeah, this is different. That's just for the computer sign out. This is just so that I know who was here today. Okay, let's talk about let's talk about some statistics now. Major components of statistics, as I see them, are design, where you haven't done an experiment or a study yet; description, which is the first thing you do when you get new data to help you get a feeling for the data and to visualize it and put it in tabular form, just to understand what you have and notice any sort of big gross characteristics of the data; and inference, where we actually make decisions. There is a fourth one, which I probably should have mentioned on this slide. Hello. But that would be prediction, something that I do a lot of, which could probably be separated out from inference, and is when we're specifically interested in making predictions of future events. Statistics, to me, it's much older than science. In fact, it is in some ways a science, but it also in some ways predates science, and it is the most basic methods of understanding data, whether or not it came from a scientific experiment. And we have records of statistical methods that are still in use today, going back to 450 BC, calculating the mean. So these are some of these methods that we cover in this course. They're truly timeless and are at the very base of understanding numbers, making sense of them. Some definitions. So I'm going to talk about a population, and that has a specific meaning in statistics. And what I mean by it is the entire group of interest. So a population could be all people in the world. It could be some subset. It could be American adults, so not everyone, but it's still defined. It is some group of people who we are interested in, and it is all of them. Or it could be like the residents of New York. But the important thing is that this includes everyone who we're interested in and whom we would like to understand something about through our experiment or through our study. Whereas a sample is just a selected subset of that population. So most of the time we can't observe everyone in a population. We have limited funds, we have limited time, and it's only practical to look at some small portion of that. And this is what we will call a sample. So this was a study that I saw shortly after I moved to New York that I thought was interesting, where they had determined what the world's favorite city was for a number of different things. The world's favorite city overall was New York, which was heartening since I just moved here. But not as much to live, which I learned why once I tried to find an apartment, and so on. So it doesn't exactly say here, but it does say, let's see, survey covering 18,000 people in 24 countries. What do you think the population was for this study? What's that?
Millions of people.
But what is it?
The total number of people in those 24 countries.
Yeah, that is one thing it could be. I mean, yes, it is doubtlessly millions of people. But when I think about what is the population, the thing that I usually want to be clear about is who those people are. And so one way to look at it here is that it is all of the people in these 24 countries, whatever those countries are. Based on their conclusions here, like world's favorite city, I would say that the population that they had in mind is everyone in the world, not just in these 24 countries. And probably they chose those 24 countries as a sample of all of the countries in the world, hoping that it would be somehow, or assuming that they would be somehow representative of all of the other countries, and that they would be able to generalize based on those 24 countries. And they sampled, by the way, a lot of people, 18,000. That's a very large statistical sample, I guess, covering, aligned with the fact that they are trying to cover a lot of different demographics and countries. As a note, something that I will really hammer in later, it turns out that in statistical methods, you normally don't need samples like this, no matter how big your population is. Your required sample size is independent of the population. And in fact, it is much more important that your sample is representative than that it is large. So a very large sample, but that is very biased, say they just put something out on the internet and let people fill in this online form, that's going to be a biased survey. And so no matter how many responses they collected, it's probably not going to be very reliable, because maybe New York just, I don't know, had a big Facebook call go out and everyone voted that, yes, I like New York. And so maybe most of those 18,000 people came from New York. I don't know. Probably not. Probably they're all not from New York. If you did measure all of the people in your population, by the way, that's called a census. Something that happens every how many years? Every 10 years in the US. And each one of these observations, so each one of these 18,000 people is called a record or an observation. Those are interchangeable. Descriptive statistics are what they sound like. They're just ways of describing the data. So I feel like sometimes this doesn't get sufficient credit as an area of statistics, but it is a very important area of statistics and a very important part of your data analysis. And I include this. This is a famous example, just to show this conquest of pestilence in New York City, just to show how much information can be conveyed in a good descriptive statistical graph. On this one sheet of paper here, we have covered, we have a couple hundred years. We have the deaths per 1,000 population going up and down, and then some spikes, which are labeled by what that increase in death rate was attributed to. And you can see this trend going down and down over time until there are no, after 1918, there are no big spikes and no great pestilences in New York City. So even though there have been no inference tests, nothing formal done on this, you really learn a lot from it. And in fact, you probably learn more from this than you could from any hypothesis test or any of the other more mathematical approaches to analyzing these data. And there are no doubt quite a few mathematical approaches that you could take to it. So the final part, and I did skip over design because we don't really cover it in this course, but we do cover plenty of inferential statistics. And inferential statistics are where we have some limited amount of information in our sample, and we want to make inference about the entire population. One very well-known example would be polls, where the pollster wants to make some kind of prediction or inference about how the population of voting adults will vote on election day based on calling up 1,000 people. This is, we all know about some of the problems that come from polls, but they're also pretty useful and pretty amazing when you consider that this small number of people can give a reasonably accurate prediction about millions of people nationwide here. And here are 4 different news organizations trying to estimate Obama's approval rating. They all used somewhat different methods. They all called different people to ask, and they all got more or less the same results. So it tells you that, you know, there is a lot of value to be had in this sampling approach. But the questions, so this is just sort of plotting the lines, the results that they got. The questions where we're going to cover things to give additional information are questions like, how great is the uncertainty in here? So, okay, it's one thing to say the approval rating is 40%, but how much uncertainty do you have in that? And what are the sources of that uncertainty? We do samples and inference on those samples to answer questions like, does an experimental treatment for cancer work? Because you can't just try it on 2 people and say that because it works on 1 person and that it is an effective treatment. There's random variability between people. You need to get some kind of an estimate of the efficacy of a treatment on the population through randomized clinical trials. Cycling in the city, is it becoming more dangerous? Well, who city? Nobody. But you might be able to look at a sample of all of the events, or even if you have traffic data and can look at all of the events, you might want to look at trends over time and analyze whether the variations going up and down are just consistent with random variations, or whether there seems to be a trend occurring over time. Or do public health issues vary across the city? There are some very good City of New York. The Department of Health and Mental Hygiene makes publicly available data sets that you will have the option of using for your project, and you'll learn a little bit about this semester that can answer questions like this. And if you have anything else that you're interested in or you're wondering about, feel free to post it to the group. All right, I'm going to give you an introduction to classes of data. Any data that you analyze, almost any data. Maybe there are some exceptions, but you will probably be able to categorize it into one of these 4 types, and being aware of what your data type will help to make sure that you use appropriate statistical methods and don't make mistakes when you analyze the data. And there are plenty of opportunities to misuse statistical software if either you are not sure what your data type is, or you're not sure to code it correctly in the statistical software. So nominal data, further split up as binary / dichotomous when it has 2 possible values, or categorical when it has more. So some classical binary or dichotomous variables, at least in terms of how they are analyzed in statistics, could be sex, male, female, or the survival for people suffering from a disease, alive or dead. And the reason these are called nominal is because they're not really numbers. They have meaning, they're words, but they get coded as numbers by statistical software and treated as numbers in analyses. But they are different from actual numbers. They're nominal variables. Categorical variables are the same, except you have more than 2 types. Say blood type. We've got 4 of them. And this would be one way to code a categorical variable. There are actually other ways to code them than this. So we call them nominal variables because they're only nominal numbers. We might assign them numbers for convenience, but they're not. They're words, they're things, they're ideas. Ordinal data are similar to nominal data in that they're categories, they're not really numbers. The only difference is that they have a natural order to them, such as the Karnofsky performance scale to describe the health condition of a patient, where 0 is fully active, healthy, 1, 2, 3, 4, where 4 is completely disabled and unable to move on their own. So it's again a nominal variable, but one in which there is an order. That's an ordinal variable. So the order of these is important, but the magnitude is not. There is, we can't say that the difference between fully active and can do light work, that's not half the difference between fully active and no work. Like they're not necessarily equal steps. They're just ranked. And rank data is a type of ordinal data. For example, the outcome of a running race, where you might have a first and second place finisher that are within a second of each other, and the third place finisher is a full minute behind. So the difference is not necessarily the same. It's only the order or the rank that is important. Some data you could think of in different ways. The leading causes of death in the US, you could think of this or talk about it as rank data. If you want to talk about heart disease being the leading cause of death, cancer being the second leading cause, and lower respiratory diseases as the third leading cause. So when you're talking about ranking them there, they are ranked. Of course, if we were talking about the actual numbers, then it's not ranked data anymore. And again, the magnitude of the differences here don't matter. It's clear there's only a 23,000 person difference between heart disease and cancer, and a much larger difference down to the third place in deadly diseases in the US.
So,
Yes?
What's the difference between the regular ordered data or the ranked data?
They're the same. Ranked data is just a type of ordinal data. Rank just means that we've taken some continuous or discrete variable like this and ranked them by their magnitude. Whereas ordinal could be something like that Karnofsky performance scale, where it's just it's ordered. You could think of it as rank as well. So it's not an important distinction between rank and ordinal data. Usually rank is used when you talk about converting a continuous or a discrete value like this into their ranks, like time to finish a race, number of deaths, things like that.
The order is based on, there's some order to it.
Yes, that's right. So it's still ordinal. It's still ordinal data. In terms of if you're going to analyze rank ordinal data, it would be the same. It doesn't matter. It's really just common nomenclature. All right, so the first two types, not really numbers. These last two types, discrete data and continuous data, are actually numbers in the sense that we usually mean them. So looking at these same data and looking at the actual number of deaths, this would be an example of a discrete variable because it can only take on integer values. That's what makes it discrete. It can't take on any value. But it is a number in the sense that we normally think of numbers, and we can do arithmetic on them. We can add them, subtract them, multiply them, things like that. So that makes them real numbers. So if looking at this now, we're talking about not just the total numbers on there, but actually deaths per 100,000, and they're also age adjusted. So they've taken the distribution of populations in these different years. So maybe if there's an aging population, you have more old people in 2011 than you had in 2002, or if there's a lot of, there were a lot of new births at some point, then maybe you have more young people later. Age adjustment is a way of correcting for that, and something like heart disease that affects older people much more than younger people, it's adjusting it to the same population distribution. And here they're still being listed as integer values, but there's going to be decimals, a lot of things. This is where it starts getting a little bit messy as to whether it's really discrete or continuous data. And in fact, it doesn't matter that much. And we're really not going to try to trip you up as to what is discrete and what is continuous. In some cases, it's really obvious when it's just a count. In some cases like this, it's a little bit less obvious. You could treat it as or talk about it as discrete or talk about it as continuous. The statistical methods that you would use are the same in either case. So that's my point there, that the discreteness becomes pretty unimportant when you have many possible values. When you're talking about thousands of people, millions of people, the discreteness doesn't matter. It really only matters when you have a small number of people, such as, say, number of children in a family, things like that. The discreteness becomes more important. And again, the magnitude here orders, so 4 is twice as big as 2, and arithmetic applies. It means something to say that the rate is 5 times as high for cancer as it is for pneumonia and influenza, for example. Yes, there's a question.
The discrete data, is it valid like for the year? Because let's say you said like 16 children per 100 inhabitants. So is that, let's say, for the next 5 years, the population grow? So is it still valid, or it's fixed for a certain amount of years? I don't understand that.
So I think you're asking about the age adjustment, about how and how the age changes over years. So
okay, let's say if you have that data for 2002 to 2011,
yeah,
can we use it in 2016? Because it gives you
Yeah, I mean, that is the whole point of the age adjustment, to make these directly comparable across years. Because the problem is, if in 2002 your average population age was 35, and then in 2016 your average age was 45, then without the age adjustment, you couldn't directly compare them, because it would look like you had higher rates of all of these diseases in 2016, and everyone's health was getting worse in 2016 than it was in 2002. But the age adjustment, you calculate rates for each age group and calculate what it would be in a reference year. So it would be like taking the distribution of ages in 2016 and calculating what the death rate would have been in 2002 if the rates in each age group were the same. So of course, the purpose of age adjustment is to compare across years or across states or countries that have different age distributions. If what you care about is, in fact, just how many cancer deaths there are in absolute terms, because you need to have the right number of hospitals, of the right amount of treatment drugs, then you're not going to use age adjustment, because it's not the actual amount of people in this year, it's in a hypothetical population. Good question. So finally, continuous data. These things like time, weight, length, mass. You could argue that all continuous data are in fact discrete, because the things that we use to measure them are discrete. If you use a stopwatch to measure time, it probably only goes to 0.01 seconds. If you use a scale, it's only going to measure to the nearest pound or half pound or something like that. So it doesn't really matter. In theory, these things are all continuous. Meaning that so they can be bounded, like weight is always greater than 0, time is greater than 0, but all possible values are available in between those bounds. So you can have any number of decimal places, and there are no forbidden values between those bounds. And again, like discrete data, the magnitude of them matters. So twice as big means something, and arithmetic applies. You can multiply them, you can add them, you can subtract them. Summarization, yes?
One question about between discrete and continuous data. So
yes.
When I'm thinking about it for discrete data, I think about like cases of glaucoma. You can't have half a case of glaucoma. You have to have one. But continuous data, you can't have like.
Well, whether or not you have glaucoma, that would be a nominal.
That's nominal.
That's nominal. If you are, if for each one of your records, your data is whether they have glaucoma or not, then that is a nominal variable. Whereas if your data, let's say your records, each record is a county and or is a block or something like that, and it's the number of glaucoma cases in that observational unit, then it's a discrete variable.
I meant like things that can't have intermediate values, like have to go in certain chunks.
Yeah, and if it can only have 2 values, then it's nominal. If it can have more, and you're actually counting, then it is discrete. Is there another question? Yes.
What is the ratio or interval?
What is ratio or interval data? I would use those synonymously with continuous data. Intervals referring to the fact that it's between some interval, ratio referring to the fact that you can take ratios of them, you can divide, and if there are decimals, that can be described as a ratio. So just more words for continuous data. So descriptive statistics and summarization of data are, in my opinion, very, very important and possibly the most important part of your data analysis, because this is where you become familiar with your data set, where you gain some intuitive understanding for what you have and avoid coming up with statistical inference that is illogical and that doesn't match with things that you can clearly observe in the data. And there are lots of ways to do it, and there are various options for every data type, both in tabular numeric form and graphical form. Getting a little short on time, but I think we still have time here. I'm going to break these down again by the data type. So for nominal and categorical data, we could use a pie chart. Anyone see? There are a couple things wrong with this pie chart. Any feedback on what's wrong with this pie chart? Yeah, so we have 87% and 13%, but they look the same here, so that's a problem. I don't know, any other problems? The other problem is not actually a problem with this pie chart in particular. It's a problem with pie charts. Yeah.
The presentation of the size of the percentage?
Yeah, the presentation of the percentage is all wrong here. This looks like 50-50. But you know what, even if they had done this correctly, yeah?
With more data sets, so say there were like 15 choices, it's harder to tell the difference between each of them without a number associated.
Yeah,
so you look at a bar graph, you can see the trend of the bar graph very easily. You look at a pie chart, it's hard to compare.
Yeah, that is exactly right. And I'll just summarize that before I was going to say there's no sample size in this group, at least. Yeah, okay, so two very good points here. The first one was that if you, it's actually kind of hard to read angles. It's pretty hard to tell the difference between 20 and 25%, or especially between say like 35 and 40%, especially if you start getting a bunch of slices of the pie. A bar graph is much more informative and quantitative, and you can actually compare directly, whereas it's very hard to compare angles. And the other good point was that there's no sample size information here. So we don't know if this is 100 people. We don't know if this was like 6 people and 5 said yes, 1 said no. It's unclear from this plot. So using the same amount of space, you could be a lot more informative than this pie chart. And in fact, pie charts are a pet peeve of most statisticians. And I'll never ask you to do one. A better option, first thing for nominal or categorical data is just a frequency table, which are also called contingency tables. And it's not nearly as fancy as what it sounds. All it is counting your total numbers for each variable. And sometimes you will put both counts and percentages, but that's all it is, just the counts. So for example, we had a clinical trial where we enrolled 100 people and randomly assigned 50 of them to treatment and 50 of them to control. This is the contingency table for the treatment group. It's just 50 and 50. And if of those 100 people, there were 20 who reported mild pain, 30 who reported moderate, and 50 who reported severe pain. That's the frequency table or contingency table for severity. So simple, but it does take and compactly give yourself or someone else reading your report a quick idea of what your data set includes. And in fact, this is more complicated versions of this are very, very commonly table 1 in any epidemiological study. It's just giving the frequencies of who is in your study, so someone can look at that table and understand who your sample is. You can also do these for 2 nominal or ordinal or categorical variables. And then instead of just a single row, you have multiple rows. So here, this is showing, say for that same imaginary clinical trial, it's actually showing how among the treatments and the controls, the distribution of amounts of reported pain is different. So you can look in the treatment column, the control column. As an aside here, I've written down the sums in the margins of this table, and they look at the same as those one-dimensional frequency tables on the previous slide. And these are called marginal totals, and we will use that some more. And it's just because you would add those up and write them in the margins of the tables. And you can convert these to probabilities. So here, instead of 50 and 50, it would be 0.5 and 0.5, and here it would be 0.2, 0.3, and 0.5, and then those are called marginal probabilities. So these are marginal totals, marginal probabilities. This is a two-way frequency table or two-way contingency table. And yes, there are the marginal probabilities. I keep forgetting to do the slide builds. Graphically, you can represent these same things as bar charts. So these are the equivalents of those one-dimensional frequency tables done graphically. I would probably, in this case, recommend doing them just as a table, but different people have different preferences for whether to represent things like this graphically or numerically. And it's also possible to do an equivalent of that 2x2 table as a stacked bar chart. So here we have the 50 treatments, the 50 controls, and you can see the proportions of people reporting the different severities of pain for each of them. So now it's nice and graphically, you can quickly see that in the control group, you have more severe pain and not very much mild pain, and you have quite a bit more mild pain and less severe pain in the treatment group. All right, so for our discrete data and continuous data, a first tool is so-called frequency tables, which the same thing except where we put the data into bins. And this is again often how in that table one where you're reporting the frequencies of your nominal and categorical variables. You'll often see the same thing done for continuous variables, except that they're put into bins to make them categorical, and then they're reported in the same way. So if this pain scale had been discrete on a scale of 0 to 100, and then we arbitrarily bin those into 0 to 30 being mild, etc., you'd end up with the same type of table. And of course, smaller bins means just that you have a bigger table. And the histogram is a graphical representation of the same thing. This is instead of, so we've taken that continuous scale from 0 to 100 and put it into bins of 2 here. And instead of writing out all of these frequencies, we're just putting them onto this single plot. So this is a nice graphical way of summarizing a continuous or discrete variable. And that number of bins is really subjective. Sometimes you can get different looking histograms depending on how big you make those bins, which is just, it's good to keep in mind that in descriptive statistics, you're making decisions of how to represent your data, and those decisions will affect how it looks. So it's not an objective, one way to do things process. It is a subjective process, and even if all software will have defaults, it will try to choose your width of the bins wisely, but you can change those defaults, and if there's something about it doesn't seem right to you, you should be ready to change it and try visualizing it a little differently. So this is just by way of saying that in this particular example where I simulated scores between 20 and 80, if I used any particular cutoff for mild, moderate, or severe, it would have been arbitrary. There isn't any clear distinction between people at 39 or 42. And it is generally good to try to use your data in as close to its original form as possible, rather than losing information by creating arbitrary bins like this. There are a couple decorations you can add. These are called frequency polygons. This is a probability density. These allow you to put more than one continuous variable onto the same plot because you're just using a line. Box plots. These are really wonderful plots, and ones that get, I think, underused by a lot of people because they provide less detail than a histogram, but they allow you to put more variables, to put more things onto the same plot. So here's an example with a probability density line that I put here instead of the histogram, and I've put the corresponding box plot just above it. To understand a box plot, you need to know what a percentile is. It's just the percentage of the values that are below any given value. Like if you score in the 90th percentile on the GRE, it means you did better than 90% of the test takers. These quartiles are just the 25th, 50th, and 75th percentiles. And they're shown on the box plot by these three lines. This second one has a special name. It's the median. And these are the first and third quartiles. And this difference between the first and third, that's called the interquartile range, or IQR. And this is a robust measure of the spread in your data because it's not changed by outliers. It's just where the middle 50% of your data lie. Pardon me. These things here are often called whiskers, the things on the out here, and these are placed by convention at the median plus 1.5 times the interquartile range. So you go from the median, you go out to this first IQR, and then you add another 1.5 IQRs to that, and you place the whisker. And then any data points that come outside of that get plotted individually, so it shows you it's one way of thinking of an outlier. So a lot of information in just this one little box. Sort of probably the most detailed representation you could give of a continuous or a discrete variable would be to actually just plot every single data point, which is usually too much information. It's kind of hard to actually get a lot from this because it's too much. There's not enough summarization being done here. But there are fancy plots. This, I believe, is done in SPSS, but where you combine all of these different things. You've got the histogram, the probability densities, you've got the individual data points, and you've got a box all in one plot. It's a nice graph. So this is just one continuous variable, vehicle horsepower, shown in a lot of different ways. So just to wrap up, remember you've got nominal and ordinal data. These are the ones that are not really numbers. Ordinal data has a rank. You can use frequency tables. You can use frequency bar plots for those. And for the discrete and continuous data, the ones that are actually numbers that you can count, that you can add, you can subtract. Use further discretization to make frequency tables of those as well, and bar plots, as well as histograms, box plots, and some of these other things, the density lines and the frequency polygons. If you are going to plot them without any further discretization, we haven't gotten into bivariate stuff yet, but there are scatter plots and there are strip charts. So just so you know, those of you who are interested in learning R, I've posted in Blackboard and here the code that I used to generate all of the plots in these. Afterwards, with Tony, you'll be making a bunch of these plots using SPSS. And that's the end of lecture for today, almost on time. Are there any questions before I shut it down and we take a quick break and we'll switch over to lab? All right, thank you. That's